shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Welcome to the webinar. The webinar will begin shortly. Hello everyone and welcome to the webinar. My name is Bob Went and I shall be the moderator for this webinar. The webinar is entitled Reducing Leak Detection OPEX by Implementing Real-Time Hydraulic Simulators of District Metered Areas DSMs, and it will be presented by Glyn Addicot of Hydraulic Analysis. There'll be a short time for questions and answers at the end of the presentation, but please note that the presenter's details will be shown during the Q&A session for you to make a note of them should you wish to follow up or ask Glyn any questions that you didn't get the chance to ask today. Please post your questions during the webinar using the Q&A button in Teams. Details of the next webinar will be shown at the end of this presentation. Thanks very much, and I'd now like to hand over to you, Glyn.
Thank you very much, Bob, and hello everybody. Hopefully you can all see my screen. Yeah, I appreciate this opportunity to speak to you all at the this year's Water Equipment Show. It's a shame it's not face to face, but I look forward to getting back to normality. So I'm just going to take you through sort of a really interesting project we've been working on in the UK, which we're now implementing much more widely regarding reducing the costs of leak detection and tuning hydraulic models and real-time hydraulic simulators, or digital twins, as everyone seems to call them these days, to actually help to find leaks. So digital twin, it's a buzzword at the moment, and it can mean in all sorts of things. I'm not a big fan of it, but I accept that it's common terminology now. So our digital twin, how does it work and what does it do? So effectively, it's a real-time GIS-based transient pipeline simulator, which is a bit of a mouthful. But effectively, we build a hydraulic model of a district metered area DMA using our software, which we've used for surge analysis for the past 50 years, and we drive it with live data from the asset to give a complete picture of the DMA to monitor it. So first of all, you can monitor the DMA for leaks and bursts. We also incorporate other technologies such as acoustic logging to find existing leaks. The main advantage then, though, is once you have this replica or this twin of the DMA, you can then carry off desk-based studies to optimize it and reconfigure it to reduce pressures and reduce leakage. Now, the key real driver for this for us is not necessarily just finding existing leaks. It's obviously important, but it's understanding why leaks are occurring, and one of our key strengths is looking at the effects of pressure transients and surge pressures on this DMA. So we can actually pick up pressure transients coming into the DMA from the wider supply system. We track them, we can show where they go through the DMA, how they propagate, and also then we can show that these actually cause leaks. And this first pilot we've done has been a fantastic opportunity, and we've got undeniable evidence that pressure transients are causing leakage. And then also once you find the leaks, then it allows step testing to be planned and tested out as well. So you can actually use it as an operational tool. So let's talk first of all about visualizing data. So we're at a great point in the industry and technology that we can actually view data in many different ways. And our online hydraulic simulators are used all over the world. So in many countries, we have a contract at the moment for building a twin of the whole water supply network of Qatar. So an entire country, an online hydraulic model, which will run in the control center. We've been doing that, and we've been doing this for 5 years now in Dubai. And you can see that the top picture here is a screenshot from our simulator of the entire water network of Dubai. We've built models on the gas systems. In this case, this is the gas distribution network of Western Europe. We built a twin of that, but also we can show things very cleverly like animation. So this is the elevation profile of a DMA, so you can see actually how the topography and ground changes in your district metered area to understand why you have higher pressures in one area and not in the other, and it gives a very clear picture of how the DMA looks. So there's 3 main steps really to create this DMA, and it really isn't an awful lot of work. It sounds like a massive undertaking, but we've got this pilot project. We've got the twin up and running in less than 3 weeks. So first of all, we take shape files. That's JS shape files of networks from the water company, and then what we do is then combine these shape files with what data is available. So we're very fortunate in the first pilot for Thames Water that we've had smart metered customer demand, and this wealth of opportunity we're getting with smart meter data now is just brilliant. But we can also use billing data, and then we'll assign these demands to nearby nodes. So we don't model every house, but we group them together using the nearest neighbour method. So the twin can run fast enough to keep up with real time. And then we basically drive it with whatever data is available. I mean, you have district metered flow data. We include the PRVs, the characteristic size of the PRVs. We model the PRVs controlling, so as the PRVs just stroke position in reality, so they will do in the twin. And we also include the DMA boundary point, so we close off the model at these boundary points. And then effectively the next step, which is the only real equipment needed, is we then introduce standard GPRS pressure loggers across the DMA at various locations, and then we take that pressure data from the logger manufacturer, which is HWM in this case, and we drive that into our twin through an API link. So basically we just soak up whatever information the water company's got, and we bring it into one single platform. And once you do that, well, you have a wealth of opportunities then. So initially the twin will undergo a calibration procedure against pressures and flows. So we'll try and understand how the DMA operates, and the twin will reflect the continual day-to-day operation of DMA, and also include background leakage, because obviously leakage is a very important factor, so we can include leaks. We'll first of all show the source and distribution of water through a DMA. So if it's got multiple feeds, you can see where that water goes, where it travels to, and where it mixes. We can show areas of high pressure, and then potentially allow the DMA to be reconfigured to actually reduce these pressures. And also we can use it for supply interruption work, which is where we can identify which critical valves in a DMA. So there might be 1,000 valves in your DMA, but probably only less than 100 will be critical for operations. And we try and then make sure that these critical valves are the focal point of maintenance efforts, such that if there ever is a burst in the DMA and operations need to go and isolate a pipe, then if you know that you've got a number of critical valves that are always going to work, you will guarantee that you will be able to close off that pipe at a certain point and minimize disruption to other customers. So where you have these big supply interruption events, it's often because valves can't be closed. You end up having to widen the net and isolate more customers. And what we'll typically do is say, well, if your minimum customer number is 50, if you maintain these 40 or 50 valves in the DMA, then you'll guarantee that if you ever have to isolate any one pipe in that DMA, you will only ever cut off a maximum of 50 customers. And then leak detection, which is obviously a key part of water industry targets in this AMP phase. So the digital twin calibration starts initially significant pressure differences, or we call them errors, between the twin and reality, as we've not got leaks in. So we don't have these leaks initially modelled. So there's more flow entering the DMA than leaving, because we've got the district meter flows putting this flow in, but we've not got it coming out because we've only got customers modelled. And then basically where you have these pressure transducers across the DMA, where they show the biggest error, or the difference between the measured value and the simulated value in the twin, so where there's the biggest disparity, that's the most likely area where there's leakage or unknown consumption. And then what we can do is then we start to actually then implement leaks into the twin various pipes until we get a match. And so once you start getting that match, you've got a good idea that this is where your leaks are, and then you can commence with either step testing or traditional leak detection methods. So it's a very powerful tool for locating the areas of leakage very quickly. Yes, it's not going to fine tune it down to a street level, but it'll give you the area of the DMA to focus on, which will typically be 10 or 15% of the area of the DMA where your big leaks are, because they're causing the pressures to be lower in reality than they should be. So leak detection capability. So we've partnered with this service with Morrison Water Services, and I have to say that they've just been a fantastic partner for us on the ground. They've left us to get on with the techie bit, if you like, and they've helped us with field testing, with checking valves, with supporting leak detection, and they've been an absolutely superb addition to our ability to implement digital twins. And we're actually have a partnership agreement with Morrison Water Services across the UK for this. And we're trying to constantly find different ways and to implement techniques to find leaks. And what we're trying to do now, very successfully, is to actually combine acoustic data, sound recordings, with pressure data, and therefore you have two completely independent methodologies used to be able to confirm the presence of leaks. So if your pressure loggers are indicating that there's a pressure imbalance in the system at a certain area there shouldn't be, and your acoustic loggers are alarming, then you've got very, very high confidence levels. You've got a really significant leak in that area. But also we've proven it can automatically detect bursts and large leaks as soon as they occur, and typically within minutes, as soon as we get the data coming in and there's these pressure changes, the twin will show you where the leak, the burst is. And our idea then is to allow water companies to get to site very quickly before they get the inevitable phone call from the customers. Just some of the graphics we've got. So this just shows the demand. So we've got a heat map here. The darker areas are the bigger demand. So first of all, in a DMA, it will show you where your biggest users are and your biggest demand. So it's a very useful operational tool to understand, you know, the critical parts of your DMA for usage. At velocities and flow direction, you can see where flow goes in the system. You can see what velocities you've got in the DMA. You can understand how the flow travels, or the key arteries and the transmission parts of the DMA. So you can picture very easily where your flow and water travels to in the DMA, and also how long it takes to get through the DMA. So you can then look at age of water, water quality. Flow source, so basically where does your water go? So in this particular DMA, we've got 3 different district metered feeds into it, and you can see that the water's coloured, and where the colours change is where the boundaries are, where you get more than 50% concentration of a water source, and that just allows you to see where your water's flowing. But probably the key bit for us from the very beginning has been pressure transient. So the focus of this is always good to find existing leaks, but we really need to stop these leaks occurring. We need to understand why they're occurring. Being able to predict a burst a day or two before it happens is obviously a really powerful and useful tool, but you know, our plan is to actually, you know, really reduce the number of leaks and bursts that occur in the first place. And it's pressure transients, and it's generally accepted now. There's been many universities have proven the links between pressure transients and bursts, and this has been a really powerful addition to our arsenal for our digital twin. And what we've got here is actually a pressure transient that we picked up entering our DMA from the wider supply area, so in the trunk main. So there's a pressure transient that periodically happens every couple of months, and you can see the path that it takes through the DMA. You can see where this pressure transient goes. So we pick these up on the pressure loggers, and then we can model and track them. We can actually show every pipe that's affected by these pressure transients. The power of that is really in this graphic. So for this particular DMA, you can see there's a heat map of all the different repairs they've done over in this DMA over 3 years. And then what you do is you cluster the most significantly statistically significant leaks and bursts, so the most reoccurring ones and the biggest ones. And you can see here that it's right in the path of these pressure transients. So it goes to show this exactly where the pressure transient slams into. And certainly the highest leakage areas in this DMA are where this pressure transient goes. And we've now taken steps to actually eliminate this course of this pressure transient. We actually expect now over the next year or so that the leakage levels will really drop quite significantly in this DMA, because we're calming the DMA. We're dealing with the pressure transients. We're solving getting to the root cause of leaks and bursts, not just finding them. Find and fix is great; it'll always have its place. But our idea is, if the water companies really want to actually tackle leakage properly, you need to stop these leaks and bursts happening. And pressure transients are without doubt the main cause of leaks and bursts. Yes, there's other things like other services interacting with the pipes. There's traffic, ground loading, but pressure transients are one of the key factors, if not the largest factor associated with leakage. So what's our digital twin delivered so far? Well, it's many different aspects we've done with this, and first and foremost for me, the most important thing is we take GIS data from the water companies and we clean it up. So first of all, when you get these shape files, you have floating valves, you have pipes that aren't joined, you have disconnected pipes because of the way the GIS data is recorded. And what we'll do is we'll take these shape files and we'll connect everything up. We'll get them accurate, we'll get them healthy. Because if you don't have, it's garbage in, garbage out. If we don't start off with good, reliable data in terms of pipe diameters and lengths within our digital twin, then we're not going to be able to help understand the operation. So we've got these shape files now cleaned up, which the water company will get, so they'll know where their valves are, which pipes the valves are connected to, their fire hydrants, and you get this very clear picture of GIS data. And then once you've done that, we give a live picture, the pressure, flow and water source, every location in the DMA. And it doesn't matter how many, I've been doing pipeline hydraulic modeling for 25 years, but it doesn't matter how many times you look at a picture of a DMA on a piece of paper and think you know how it operates. It generally doesn't. It's that sort of re-educating yourself on how these systems actually operate, where flow goes, and how the pressures change over a day-to-day period. You can also then look at demand changes. I mean, it's very interesting the past 12 months for us, because we've had COVID issues. So we've had COVID flow demands, which have caused significant changes in demand patterns, which we've incorporated into the twin. We've obviously it's Eid today, so we've had Ramadan for the past month, which, as everyone knows, can change the flow patterns in DMAs. So it's that clarity of data. I've already mentioned that we've identified and tracked an incredibly damaging pressure transient entering the DMA, which is now being eliminated. And that once that pressure transient has been taken care of, then we'll be in a very strong position to actually see the leakage levels drop. We identified a zonal valve that was passing, so we had a breach in the DMA. The twin identified a breach, and also there's over 1 megalitre per day leakage as well, which has been identified. We've also then looked at solutions to reduce unaccounted for water by 1 MLD by optimizing PRVs. We're looking to actually divide this DMA up and create a smaller sub-DMA fed by a single PRV, and we can then dramatically reduce the pressures in the area, both at night and during day. And obviously you reduce the pressures, you reduce the leakage, but also that change in pressure really helps us then to find the leaks using the acoustic approach we've taken as well. So it's that ability to make the DMAs healthy and repeatable. It's fantastic, and the list goes on. I mean, I honestly did not have enough space to put the bullet points in here of what we've achieved, because we've identified bursts before they've happened. So the burst, we could given 24 hours notice the water company of this burst. Then as soon as the burst occurred, it's alarmed and alerted to the burst. We found countless closed valves in this DMA, because over the years, obviously, as network operations take place, valves are left shut by accident, or they can be broken shut and have to be repaired. And the number of valves that Morrison have found and repaired in this DMA has been staggering, and we're still finding them now. But what that's doing is it's opening up the arteries of the DMA. It's improving the distribution of flows, and it's making the DMA healthier. And that's all what this is about. It's about this healthy data and this ability to understand. And these digital twins will run live. So our dream is to actually install them in the control centers and data factories of water companies. So they actually just sit there 24/7 running live. It's not like an offline hydraulic model where you have to pick it up and try and calibrate with data. These will just run 24/7. And that's the real strength of our software, and where we've proven ourselves all over the world with our simulators is the accuracy levels that, we've got applications from China, Australia, Europe, Africa. These digital twins are proven and robust. We've got them in all sorts of pipeline applications in Saudi Arabia. I've always mentioned the UAE, Qatar, Kuwait. So our twins are proven. This is not a new technology for us. It's basically just taking live data, and that's the beauty of where we are now in the water industry. Is we've been putting our real-time simulators in oil and gas pipelines for nearly 20 years now, because they've always had the data. There's always been information. Obviously, there's a lot more money in oil and gas, so we've always had that data to connect to SCADA systems or API systems. But the water industry is at this brilliant place now where suddenly data is becoming readily available, flow data, pressure data, and your hydraulic model is your key point to drive all that data into. I mean, there's a lot of talk about sort of AI and algorithms, but from our point of view is what you're trying to do is you've got a pipeline network there which is sitting, and that's what you're trying to analyze. And all you have to do then is to put all this data into hydraulic models. So why just analyze the data in silos? It's taken from a hydraulic system that obeys the laws of physics and chemistry. So therefore, take a hydraulic simulator that can cope with very, very high levels of pressure and flow data and actually drive that in. To give you an example of where we are in Dubai at the moment, we have over 1 million pieces of data pass through our digital twin every minute, which gives you an idea of where the water industry is going. And our simulators can cope with huge amounts of data as quick as you can get it. There's no limitations of how much data you can feed in. The more data, the more accurate it gets. And it's this ability then to provide this operational tool. So if anything needs to be done on the DMA, you need to close a valve to do a repair. Well, you can test it out on the twin first. You can actually see what surge pressures and pressure transients you're going to cause by isolating that pipe, and therefore it might be a better way to go about that operation. You might find there's a better methodology you can take to actually reduce the effects of isolating the pipe, because we've all been there before. You try and close off one pipe and you can easily create a burst somewhere else in the system if your pressure changes are too rapid. So it's having this tool that perfectly reflects the operational system and can cope with huge amounts of data. And that's really the strength of our software. Is it's very robust, it's very accurate, it rarely fails, it can deal with just about any level of data you want, and it's proven. But really the key one here is the last point, that it's a low-cost smart network. So all we've done for this first DMA is actually install some pressure loggers. Everything else was there. The shape files are there, the flow data is there, the data's already there. It's just sat in different parts of the business. And we can either bring it, if it's centralized in one source, we can bring it into our twin, or we can bring it in separate platforms. And that's probably the hardest bit of any part of this work that we've done, is dealing with bad data and filtering and understanding data and making sure you're not driving the twin with bad data. And that's really taken us a long time to get to this point where we can handle and implement very effective rule sets to identify and deal with bad data. But this is just the start for us. You know, we ideally see this being implemented on every DMA in the UK, because this is where the rest of the world is starting to head now, and certainly in the Middle East are slightly ahead of us. But the water companies now are realizing this this is the future, and to actually take this data, the data's taken off a pipe network, so therefore the most logical thing to do with that data is to actually push it back into a very accurate hydraulic model of the pipe network. Now I know there's a number of different organizations trying to do this at the moment, but we say our strength is a factor so we can model these pressure transients, and we can deal with the pressure imbalances in the system. So if you have a steady state model and you capture data at a point when there's a pressure transient in the system, or there's a flow imbalance due to a PRV opening, then if you were to try and provide a solution to those pressures and flows in isolation, you'll generate errors because there's flow imbalances in the system. But what our software does is actually model and track these pressure changes to the system, and it can actually deal with the pressure imbalances very effectively. And that's why we're finding we're winning so many projects now in the Middle East, because it's that transient ability we have to actually deal with and model unsteady pipe systems. And that's really the point. This last point, this is that there's a lot of misgivings and misthoughts in the water industry that the water networks are steady at any point. They're steady. There's no water network in the world that's steady. It's constantly in a state of flux. There's demand changes, there's control valve operations, there's pump operations. There's no such thing as a true steady state. There's always transient behavior, and we've seen this from the pressure profiles we pick up from these loggers, is the pressures are changing constantly. They're always moving, they're always in flux, and if you can't model and cope with that in your hydraulic simulator, then it's very difficult to have a twin that will just sit there running 24/7 in a control center. And really the final point for me is you don't need a SCADA system for this. We don't need an expensive SCADA system, and we can handle GPRS data from the cloud. We can run this in servers in the water company premises. We can run it on our servers, or we can actually run it in the cloud and have web browser access to it. So it really is a wealth of different options, and we can create dashboards and bring in pattern recognition and machine learning into this as well. So this is really just a start for us, but certainly, you know, we're very, very excited about the future of the water industry and where it's going. And that's me basically finished. So I really do welcome any questions anyone may have. Then please feel free.
Thanks very much indeed, Glyn. I have a question for you from an anonymous person. Where is the simulator hosted, and who monitors it?
Okay, that's a really good question. Well, as I kind of mentioned at the end, then so it can be ideally we'd like it to be hosted and owned by the water company, and we provide training for the water company employees to operate it, whether it's in the digital sector or operations. But the advantage really of ourselves is we're not just a software supplier, but we're also an engineering company. So we'll support and through maintenance contracts them in terms of actually, if you need our advice or help in actually carrying out modifications, we can do this. So we can host it, but ideally, you know, this is the licensed and owned and operated by the water company, and this is the very effective business model in China and the Middle East. And we have you know, we have training centres as well, where they actually train their operators to run the network through a virtual copy of the system. So you can put a SCADA screen on the simulator, and then you can replay past events. You can create emergencies in the simulator and see how they react to it. So it's that training aspect as well, which is very powerful. So there's many options, but we would prefer it to be you know, owned and hosted and operated by the water company.
Yeah, thanks. A question from myself, Glyn, if I may. The benefits of the system that you've outlined are very, very clear, and there are a lot of benefits to be had from doing that. But in implementing the system, you've got a partner in Morrison Water Services, you're out on the ground, you're digging up a road, you're replacing valves, you've got the construction of the digital twin. Has there any work been done to predict or estimate the amount of money saved by going down that road and adopting this solution? It must be cost beneficial, but has any work been done to indicate by how much?
So not at the moment. No, I mean, certainly that's a question that I'd probably have to get back to you on, because that's Morrison Water Services area of expertise. But I've been told by them that it's already certainly this pilot's already provided a return on investment, because we've already identified the cause of these leaks and bursts. I mean, it probably will only be proven in time once the cause of the pressure transients is eliminated. But even in just being able to reconfigure the DMA and reduce the operational issues, so it's too early for me to say. But I've been told very favourably by our client on this that it's already more than paid for itself.
And that must be the case if obviously they're pursuing it with you and having digital twins. Absolutely.
Absolutely, that's correct. Yeah.
Yeah. I've got another question here for you, Glyn. Again, anonymous. How does the digital twin receive the data?
Okay, so yeah, that's a really good point, and that's the bit that's been interesting for us. So in our applications in places like the Middle East and China, it's through a SCADA system. So we would connect directly to the SCADA system through what we call an OPC client. So it's a communication protocol that passes information through the SCADA system to our simulator. For this particular application in the UK, obviously SCADA systems are functional, but they're not quite at the level they need to be. So we take the data through what we call an API link. So for example, for the logger manufacturer, we connect to their servers, and as the data gets uploaded onto the servers, it's squirted out to ourselves through this API link. Now, I'm not an IT person, so I definitely don't understand how this works, but it comes into this route into our database. So API protocols are the norm for us, and we can certainly handle them. The interesting points are when you have different data coming from different sources, the data might have been taken at different times, so you then have to offset when it's fed into the twin, and that's called data skew, and that's kind of quite an interesting thing. So you have to be very careful about when you present the data to the twin to make sure it comes in at about the right time. But also then again, you've got to analyze and check for bad data. So there's all these filters that come on it. Again, for battery life with loggers, obviously we can't have the loggers transmitting data every sort of 10 seconds. What we tend to do is take readings every 10 or 15 seconds, but then they're batched in 30-minute intervals. So the actual logger will only communicate 48 times a day to the twin. So it runs effectively half an hour behind real time, which is still very good. And that really does save on logger life, and we can get many years out of loggers with that approach.
I think we've got time for just one more, Glyn. What's the level of expertise required to use these digital twins in a control room situation? You were talking about having them in the control room, monitoring constantly what's going. What level of expertise or training is required on the part of operators to use these digital twins?
Okay, really good question. So about 2 days. So we do a 2-day training course, and then we have free web access, so we can usually log in remotely through a remote desktop to support them with any questions. So obviously it is that the basics you can learn in 2 days to become a basic user, but then to become proficient, there's obviously things you'll learn over time, and we're literally just a phone call away to help, and it's that support that we provide. We don't just sort of install these then walk away and say good luck. We're continually supporting them, especially as these DMAs will change. You'll have bits rezoned onto them or taken off, and we can help with that. But actually, 2 days is normally fine. Operators are very tech savvy these days. They really do know what they're doing, and they teach us as much as we teach them. So it's not an onerous or difficult product to use. It has a very user friendly dashboard. So you can also provide very simple front end dashboards for managers to quickly just look at and get a glimpse of the key statistics and key issues, or you can then drill down much deeper.
Okay, excellent. Thanks very much indeed, Glyn. Thank you for that. Well, that was excellent. Again, thank you, Glyn. Excellent presentation. Enjoyed that. Thank you very much indeed. And I'd like to thank all of you for attending the webinar as well. Thank you for that. The next 2 sessions I'm going to show on the following slide, and they'll give you details of what's coming up after this session. So I do hope you'll take the opportunity to visit them. But otherwise, thanks again, everyone, and goodbye for now. Thank you.
you.